Hi, welcome to another session of Introduction to Astrophysical Fluids. So last time we stopped just after discussing different approximations or basic assumptions in the theory of thin accretion disks, and we said that in the next lecture we would discuss the equations of dynamics of a thin accretion disk. Okay. Today, before addressing the equations of dynamics of a thin accretion disk, I would like to digress a bit and to share with you a very important physical concept, that is the concept of Newtonian fluids. Okay, so here basically you can see that if you remember that when we were talking about the ideal fluid equations, then we after deriving it, or rather after attempting the equations to be derived from kinetic equations, we also showed that the different type of forces, body forces, body force, surface force, those can be also derived from macroscopic considerations. Okay, if you remember. And we also said that the bulk force or the body force, which acts equally, equally, not by equal amount, but which acts on at all points of the volume, then this is called a body force, and the body forces are in general conservative in nature, whereas the dissipative forces are are of nature of surface force. That means they work along a surface, okay, mostly the surface of contacts. Okay, and then we said that the only type of surface force which arises in the case of ideal fluids, this is nothing but the pressure gradient force. Now here we will try to recover the form of viscous term which was absent for the ideal fluid equations, of course, and which is constituted by the off diagonal part of the pressure tensor. Okay, from we try to recover that part from macroscopic consideration. Now what we in general call a Newton's hypothesis is very intuitive, and this is based on the very basic level definition of viscosity, that is observationally it is usually found that the internal friction or the viscous effect of a fluid always tries to reduce the relative velocity between two layers of the fluid. It simply means that if you have two layers, okay, of fluid, then the faster layer always will try to accelerate the slower layer, and the slower layer will always try to retard or the decelerate the faster one. Okay, thereby in both cases, as you can easily understand, there will be a decrease in the relative velocity, and finally they want to make a compromisation between the two for becoming to a intermediate velocity, for example. Okay, and sometimes actually the global thing even comes to a rest. Okay, that is also possible. That depends, that depends from case to case. Now what in general we say that for our everyday experience, okay, so then it is true that internal friction of a fluid or viscous effect is something which always tries to prevent the development of a velocity gradient. Okay, now we try to understand much more schematically and much more systematically. That is, if we all know that the internal friction part should arise from the off diagonal term of Pij, right? That is because simply that when we worked from, when we tried to derive the real fluid equations from kinetic equations, we say, showed actually that the viscous terms are, become non-zero when we consider a perturbation or a departure from the equilibrium Maxwell-Boltzmann distribution. Okay, and this is this part which represents this internal friction, effect of the internal friction or the viscous effect. Okay. Now we try here to find the form of pi ij. Okay. Already we have done something from kinetic theory, but here we will see that without using kinetic theory, how macroscopically we will not go into the microscopic detailing. Okay, but macroscopically can we do something? Okay, and actually, historically, once again, these equations were derived much before the development of this passage from kinetic to fluid equations. Okay, so let us consider any one component, okay, of this type of tensors. Let's say I is x and j is y. Then we just consider the fluid motion, let's say in the xy plane. So this is the xy plane. Okay, and we actually consider that the z direction is perpendicular to the plane of the paper. Okay, and so in the z direction there are, that is also like, so every layer of the fluid. Okay, so y direction is the vertically upward direction along which the different layers are situated, and like the layers are basically they are flowing in the xz plane, but now we are just neglecting the z direction. We just say these layers are flowing along x directions. Okay, and if so this is, let's say this is the ground at which the flow is at rest. So the fluid is at rest because of the contact with the floor. Okay, static floor, and then it starts, the velocity increases gradually, and you can see that different sizes of the arrows simply shows that the velocities are increasing when one goes away from this floor. Okay, now of course, from common sense we say that the frictional force will work along the contact surface of different layers. Okay, and that is, what frictional force is. Even this is true when we are talking about two solid surfaces, one solid surface and one liquid surface. Okay, that is also true, and they will actually work, so mostly that will work, along this direction. So now in this case the flow is along x direction, so the friction should very intuitively work as along negative x direction. Okay, but this friction works only because the velocity gradient along y direction. If there is no velocity gradient, okay, that means the arrows are all of same size, then there is no frictional force. Okay, then from that consideration, we pose, or actually Newton posed a hypothesis, and that is the tool, macroscopic tool, to get into this business of finding pi ij, is simply saying that pi xy should be proportional to minus dvx dy. Okay, so if the differences of vx along y is more and more prominent, then the xy term of the pi tensor will also be more and more important, and there will be a minus sign because this basically tries to this developed frictional entity. Okay, this tries to reduce the velocity gradient. So in a sense, friction is something, viscous effect is something which tries to kill the reason of its generation, right? And then you can say pi xy is equal to mu times dvx dy. There should be a minus sign in general. I don't know why I did not put that. There should be a minus sign. Okay, that is reasonable. Yeah. Okay. And if for a fluid this is true, so of course we said that this comes from common sense. So in a real fluid, what we can see, okay, it is also true that this is not exactly true, but sometimes this is, I mean, reasonably true. And for those fluids, those fluids for which this type of hypothesis, this hypothesis works, is known as a Newtonian fluid. Okay. So most of our everyday fluids which we come across, most of them can work moderately well under this Newton's hypothesis. Okay. So in a sense, all of them are moderately well approximated as Newtonian fluids. Okay. So Newtonian fluid simply says that the the off-diagonal part of the pressure tensor, that is the shear stress part. Okay, so this is called the shear stress. Why it is shear? Because this doesn't have any any diagonal term. So shear simply means that shear is nothing but a combination of elongation and compression in two mutually perpendicular direction. So all these off diagonal terms are giving the shear. Okay, so this is something like a stress. Okay, you all know that pressure and stress, they are the same dimension. So it's a force per unit area type of thing, and this shear stress should be proportional to the velocity gradient. Okay, but the velocity gradient should be, okay, perpendicular. Perpendicular to the direction of the flow. Okay, that is to be understood. Okay, and one can easily understand that if we just say that this one is getting bigger and bigger, simply saying that is equivalent to saying that the frictional force corresponding to this term also increases, is also very easy to understand, because if we now write the force viscous, okay, the viscous force which is nothing but a surface type of force, okay, then that should be given by, actually this is also wrong, d of this, yeah, that should be given by pi scalared with some surface elements. And if you now see that once again there should be some d, yeah, d, yeah. Now if you do the dot product of this tensor, which doesn't have any diagonal element, okay, non-zero diagonal element, okay, when this is contracted with the area elements, okay, you will see that the x component of this viscous force simply gives you two terms. And if for our case, so we are just thinking like, the y is so we are just concentrating at one value of y, for example at one layer. Okay, so y is constant, so this part is 0, so we only have finally dv viscous x is nothing but pi xy dx dz, because dy is 0. Okay, for a given intersection, okay, for a given intersection between two successive layers. Okay, and then you can simply say that pi xy is a very good proxy, okay, is a very good proxy for d viscous x. Okay, so then that's why we say that when this pi xy increases, okay, then the reason behind this is dvx dy, its modulus increases. Okay, and it simply says that the x component of the viscous force also increases. Okay, so you see that when you have so the meaning is that stronger is your velocity gradient, stronger will be the reply of the fluid medium to that velocity gradient in terms of internal friction or viscosity. Okay. Now coming to a very practical point, Newton's hypothesis is experimentally found to hold only approximately. That's what I told. Okay. In addition, it cannot give the correct shear stress in case of rigid body rotations. That is something very, very important. Okay. Although, I mean, it is moderately valid for most of the fluids we encounter, but if the fluid is rotating, and actually if the fluid is rotating following a rigid body rotation, that means all the layers of the fluid, just now think of of a imaginary concentric cylinder, and the fluid is actually rotating in concentric cylinders. Okay. And with constant angular velocity, that means although they have different linear velocities, they don't have any relative angular velocity, so they do not have any relative angular motion with respect to the other. Okay. And that basically gives you some non-zero velocity gradient, linear velocity gradient, but the system does not need, okay, to respond in terms of its viscosity. That's what I am saying, because all the layers are moving, are co-rotating. Okay. So it is true that they have a linear velocity gradient. I am coming to that. Okay. So that's exactly which is explained here, that when the body is undergoing, the fluid is undergoing a solid body rotation. Solid body rotation means omega is constant. Okay. The angular velocity is constant. Then there is of course a prominent non-zero dvi dxj. Okay. Okay, because you can understand that if angular velocity is constant, so omega cross r, which is nothing but the linear velocity, that is of course a function of r. Okay. So that will be different at different r's. But finally, since the system is rotating in such a way that some global rotation is followed by every point of the system, so there is no need actually. So that's what I'm saying, that there is no relative motion of the layers. Okay. Of course, here we are just thinking that the whole system is only following a global rotation. There is no other flow. Okay. Then what happens, that one has to remove the solid body rotation part from the total velocity gradient. Now maybe I should explain once again that in case of solid body rotation, what happens, that we have a non-zero velocity gradient, but the viscous force is zero because there is no relative motion. So it is actually not a very correct statement if we simply say that the viscous force or the shear stress will be proportional always to the dvi dxj, but rather we should say that the shear stress should be proportional to the part of the velocity gradient, okay, which does not include the solid body rotation. How to do that? We can do a very simple thing. We can write the velocity gradient component, okay, as a sum of a symmetric part and an antisymmetric part. Symmetric part we call capital lambda ij, and the antisymmetric part we call capital phi ij, just phi ij, for example. Okay. So this is just, a plus b plus a minus b type of thing. Okay. And now let us assume that the fluid is undergoing solid body rotation. That means omega is constant. So V is equal to some constant vector cross omega, constant vector cross R. Okay. Maybe 5 minutes ago I said the wrong definition. So V is nothing but omega cross R. Okay. If I say R cross omega, sorry for that. V is equal to omega cross R. Okay. Yeah. So then Vi, okay, the ith component of the vector is nothing but equal to epsilon ijk omega k xl. Epsilon, you all know, this is a Levi-Civitas symbol. Okay. And so this is the antisymmetric tensor of rank 3, you know. Okay, and there is a sum between on K and L. Okay, now if you do del Vj del xi, so then del xi of this whole expression will go there. Just here in case it is Vj, so I have replaced the I by j over here. So now if you see, this is nothing but equal to epsilon jkl del xi omega k xl. Now omega k is constant, so it comes out. So finally you have del xl del xi. And what is del xl del xi? It is nothing but Kronecker delta Li. So if L is equal to I, then it is 1, otherwise it is 0. Okay. And if we have this type of thing, then this L will be equal to I. Okay. So finally this is nothing but epsilon jki omega k. So we now have only one sum on k. Okay. And similarly, we have del Vi del xj, which is equal to, you can show that, please check that at home. This type of exercises are super important for your own development. Okay. Del Vi del xj is equal to epsilon ikj omega k. Of course, you see this k, this is dummy index. So whether I can write k or m doesn't matter. But then when I try to write the sum again to show that what is the value of lambda ij, okay, then again I can take k for both the terms so that I can group. And if I group them, we will see that there will be this one will term wise cancel every term of this one, because epsilon jki is minus epsilon ikj. Okay, that is simply because of the antisymmetric nature of Levi-Civit's symbol. Okay, and this finally leads to the vanishing of sigma ij, capital lambda ij tensor. Okay, so it simply says that when this body has a solid body rotation, the symmetric part of this velocity gradient actually vanishes identically. So the if we want to if we want to like assign the property of the solid body rotation to some part of this velocity gradient, that will be this part. So actually this part carries the signature of rotation, this one antisymmetric part, and the symmetric part is free of solid body rotation effect, because this vanishes for a solid body rotation. Okay. And however, actually one can show explicitly that phi ij does not vanish. But how much it is? Once again, calculate this. This is super easy, because I already showed some steps how to manage that previously. Okay, when I calculated capital lambda ij. Okay, and therefore it represents the effect of rotation. Okay, so finally, removing the part of the solid body rotation, finally we can actually say that the correct statement will be the shear stress should be proportional to the symmetric part of the velocity gradient tensor, and that's exactly this one. Okay, but now we should not forget that there is another condition, that the pi ij should be a traceless, pi should be a traceless tensor. So pi ii summation over I should be 0, and if we consider that, we can actually show by some calculations that you have already seen when we were talking, we were deriving the expression for pi ij in case of kinetic theory, starting from kinetic theory. Then you know that how to do that. Pi ij is nothing but equal to some minus mu times del vi del xj plus del vj by del xi minus 2/3 Kronecker delta ij times divergence of v. Okay, where divergence of v is nothing but the trace of, so if you remember, so if you just if you just calculate this one, if you just calculate this one, so pi II, so every times you will have, so delta Vi del xi, delta Vi del xi minus 2/3, this will be 1 and there will be divergence of V. Okay, so you just calculate and tell me. Okay, but one thing is true that I mean, if you calculate, you will see that there should be some divergence of V which appears, and from here you will have another divergence of V which appears, and finally that will cancels, giving zero trace. Okay, and so finally we recover what we found microscopically. Now we find macroscopically, but for that we needed a hypothesis. Okay, and hence we see the something what we expected, and substituting now the value of pi ij in the Navier's so-called momentum evolution equation, which we call Navier-Stokes equation as well, we get that rho del v del t plus v dot nabla v is equal to minus gradient of P, so P is the diagonal element, plus of the pressure tensor, diagonal element of the pressure tensor, plus rho times G, this is the body force density, plus divergence of this pi ij. Of course, here at this point we have not considered mu is necessarily mu is constant in space. That is very general, and we will use this expression when we will talk of the dynamics of accretion disks, because in case of accretion disks, this is most reasonable it is actually found by different studies that the coefficient of viscosity is not constant in space. So this equation is perfect for studying the momentum evolution for the accretion disks. Okay, so after that we will again just come to the basic assumptions of accretion disk for recapitulation, and then I will address the dynamics of the accretion disk. Okay, that I will do in the next lecture. Okay, thank you very much.